Okay, so I don't know that this is going to be a 5 minute lesson, but I'll do my best. There is a lot to this unit. So before anything, hear me out on this part. Remember how there was that part of derivatives that we would do the old fashioned way using the limit approach? The limit of f of x plus delta x minus f of x all over delta x. The limit is that delta x approaches 0. This is very similar to that. This is going to take a long time. The problems will take you some time. You might even get frustrated. But what happened after that long limit-based process of taking derivatives? What was the next thing we learned? The rules. That's exactly where we're at. So we're trying our best to learn, like, where did integration come from? How does this work? And then tomorrow we'll start learning the rules. You already started the rules yesterday, to be honest. Okay? So what are we trying to do? We're trying to use the sigma notation. We know that very well from Algebra 2. Our graphing calculators have that feature. There's going to be 4 sigma notation equations that we need to remember. Then we just want to describe the concept of area, approximate it, and find the area using limits. So here we go. So first with sigma notation, sigma is this uppercase E looking Greek letter. It's used for sums. And if you wanted to add up the first n terms, this would be the form that you would use, okay? Next, the area of a rectangle is base times height. We need to know that. The area of a triangle is half base times height. And then here are some other shapes that we might end up need. Check this out, Colin. This should make you feel good from our pre-calc days. Look what they're doing. The method for finding the area of a circular region, they're using the exact same method for estimating pi that we used. I won't bother with going through that for you guys. And it looks like Archimedes was the first person to do that, which is sweet. We're using the same exact thought process that Archimedes used. All right, now here's the nitty gritty, okay? The black line is a function. It's a function of x, so it means y, okay? The function specifically is negative x squared plus 5. We want to find the area under that curve between 0 and 2. So using this method, we divided the area into 5 equal regions, which is why you get 2/5, 4/5, 6/5, 8/5, 10/5. 2/5 becomes our x. This right here is our f of x. Okay? And this is our delta x. So what I want you to know about this, I need to use this drawing tool, is that we are adding up, this is delta x, that's x, and that's f of x, and we're adding up delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3 all the way 5 times, okay? This becomes the basis of that. The integral sign represents that we're adding them all up. F of x is our height. and dx is our infinitesimally small delta x. We are adding up a bunch of products, and that's why our answer is an area. Okay? I think I can be pretty close to being done with this video soon, but look at the difference. On this one, we were using the right bound of our n value to get the height. Did we get enough area here? We're an underestimate here. Does everybody understand that? If we add up these rectangles, it's going to be not enough area. Notice, if we use, come on, scroll down. Uh-oh, hold on. If we use the left endpoint for this particular one, this will be the circumscribed rectangles. This one's the inscribed, in case you were wondering. And this estimate would be too big of an estimate. Yeah, Colin.
If you add those estimates together and then average it.
If you add them and average, it will give you the best estimate, but not necessarily the perfect answer, even though it does look symmetric. That's just because of the shape. This one might give you the exact answer because the symmetry, it's the symmetric nature of a parabola, but not always, okay? And then there's also a method where instead of using rectangles, you could use trapezoids. That's an even better estimate. But why are we taking all this time to do the estimates? We're not gonna, this is what they had to do before they knew calculus. But imagine, the more ends that we take, the skinnier our rectangles. So if we could let the number of rectangles approach infinity,
So the one minus n approach?
that's the limit, and that's how you get from a summation to an integration. Does that make sense?
Yeah.
If you connect those two parts, you're going to get this part. It's just going to be an annoying section for you. Basically, it's just saying delta x is your b minus a divided by however many n's you decide. Does that make sense?
Yes.
So that this corresponds exactly with this picture right. Oh no, where'd you go? With this picture right here. Here our n was 5 and our region was 2 units long. And then, oh, here we go. No exercises. Alex, did I go past the 4 important summations? I think I did.
It's in one of the earlier ones.
It is.
It's like halfway down the page.
Oh yeah, it's below this. Okay, so these you could put into your graphing calculator and it would do for you. Oh yeah, these are the 4 you need to know. So this is just the constant, factor it out and multiply it. This is what Gauss figured out. Remember when Gauss punked his teacher? If you had me for Algebra 2, that was on your Unit 9 test, I think. This is the sum of an I, this is when we have I squared, and this is when we have I cubed. These are the only 4 that you might need to memorize. And then I just wanted to show you somewhere here.
Do we need to memorize them for this class?
I think you might need to for this test, but not for this class. It should be a one-time memorization. We'll figure it out when you do your test preview, if that's on there or not. Look, oh, here it is, look. This is going back over the story that I told you from Algebra 2 of when Gauss punked his teacher. So I do think it's a true story if it shows up in a calculus book. But who really knows? All right, that's it. Boom.